Okay, let's consider another example. So we have 3 Endicott students taking turns that are rolling a die. The first person to roll a 4 will win the game. All right, we want to find 3 things. So what's the expected value, the number of turns it will take to end the game? What's the probability that the third person to roll wins? And then we have a more complicated one here. Suppose the winner gets this amount, where X is the round in which the game ends. What's the expected value of the winnings for this game? All right, so let's take care of the first one. The first thing we want to do is verify here that we're dealing with a geometric random variable. All right, so 3 Endicott students take turns rolling a die. The first person to roll a 4 wins a game. All right, so we are dealing with this, you know, in a sense, the roll of the die is the coin flip, because we're thinking of as a success. This is essentially rolling a 4, and then as a failure, it's pretty much anything else. Okay, so we do have this repeated Bernoulli trial thing, and we keep repeating the Bernoulli trial until the first person to roll a 4 wins a game. So in the first success, we end up ending the game. So this is a good example of a geometric random variable, right? So now we just need to think about what our parameter is going to be. So X here is going to count how many rolls until the first 4. And now we know that X is geometric. And as a parameter, what we can use here is the probability of rolling a 4, which would be 1 out of 6. All right, so we have a geometric random variable. Now we can deal with what's the expected value of the number of rounds it takes in order to end the game. This is just the expected value of X, so this would be 1 over our 1/6. So our expected value, the long-term average, it'll take about 6 rolls in order to win this game. Okay. What's the probability that the third person to roll wins the game? Now this one's a little tricky, because if you think about the third person, X is just looking at the game in generality, right? So the first person would win if X were to equal 1. The second person would win if X were equal to 2. Third person, X equals 3. And then it kind of repeats, right? If it takes 4 rounds, the first person wins. If it takes 5 rounds, the second person wins. If it takes 6 rounds, the third person wins. And then so on and so forth. So if you think about the probability of the third person winning, right? This would be equal to the probability X is equal to 3 plus the probability X is equal to 6 plus the probability X is equal to 9 plus ... Okay? And generally speaking here, when we're looking at all these probabilities, we're just using our PMF values. So this would be f of 3 plus f of 6 plus f of 9 plus ... And according to our PMF, we would have 1/6, our probability of success, 5 out of 6 squared, right? This would be the PMF value for the f of 3. Then we'll have 1/6, 5 out of 6 to the 5th, plus 1/6, 5 out of 6 to the 8th, plus etc., etc., etc. And we use our usual process. We think about the leading term, we factor that out. So we'll pull out a 1/6, 5 out of 6 squared. And then we'll have an infinite sum on the inside, which should we should be able to simplify using our geometric series formula. So if we take out the 1/6 and 2 copies of 5 out of 6, our second term here looks like 5/6 to the 3rd. And then over here we'll have 5 out of 6 to the 6th, etc., etc. And the way to think about this, we'll have this leading term we have 1 plus 5 out of 6 to the third plus, here's the neat little trick, 5 out of 6 to the third squared, right? So the idea is that writing this sixth power as kind of a two-step process. First, you've got the 5 out of 6 cubed, and then you're squaring it. And what you'll end up seeing is that as you increase, it's this 5 out of 6 cubed that increases in its power, right? So technically this one over here is to the first power, second power, third power, etc. So we can use our geometric series formula to simplify this. This will just be 1 over 1 minus the thing that's increasing in power, which in our case is 5 out of 6 cubed. Now we've seen this trick before, but this would end up being our probability that the third person wins. Okay, this is equal to approximately, let's call it 0.2747. All right, so this would be the probability that the third person ends up winning. Okay, so let's consider our final problem in this case. Suppose the winner of the game gets this kind of special amount. It's 100 times 1.03 to the x. So if it takes 3 rounds, we would give them $100 plus 1.03 to the third. Right? What is the expected value of the winnings for this game? Right. So what we're setting up here is an expected value computation, but we're not considering the expected value of x, right? We're considering the expected value of 100 times 1.03 raised to the x power. So by definition, this is going to be a summation of our x values over the space of x, where we'll take our function of x, right? So that's this. We'll take our function of x and we'll multiply it by our PMF value. And keep in mind our PMF looks like 1/6 times 5/6 to the x minus 1. Okay, so this is the summation that we want to look at in order to find the expected value of the winnings for this game. Now keep in mind the space of our random variable starts at 1 and then counts its way out to infinity. So this summation will be an infinite sum, and as you might expect, we're going to use the geometric sum formula again. So we're going to have to do a little bit of a simplification here, but hopefully that'll be our game plan. So we're going to write this as a sum from x equals 1 out to infinity, or we might just write out the first few terms and kind of take an approach like we did in the other case, in the previous case up here. All right, so let's give this a shot. I'm going to give us some extra space. Okay, so we're looking at the expected value of 100 times 1.03 to the x. Right, we just saw that this is going to be a summation from x equals 1 out to infinity of 100, 1.03 to the x times 1/6, 5/6 to the x minus 1. All right, so let's take a look at this in terms of the first maybe 3 terms, and then we'll do a plus ... So when x is equal to 1, we'd have 100 times 1.03. We'd have 1/6 and then 5/6 to the 0. So that would be our first term. Our next term would be 100, 1.03 squared. We'd have a 1/6 times a 5/6. All right. And then we'll have, as our third term, so we'll do one more here, 1.03 cubed, 1/6, 5/6 squared. And then this pattern is going to kind of continue. All right, so let's try pulling out, as we usually do, just the leading term so we can make it look like the summation starts at 1 here. So we'll have 100, 1.03, 1/6, all out in the front. Let's take a look at what we're left over with. We should still have an infinite summation here. We'll definitely have a 1 in the first term. And let's see what's left over in this second term. So the 100's going to disappear, the 1/6 will be gone, and 1 copy of 1.03 will be gone. So what we'll have here is 1.03 times 5 out of 6. And now let's take a look at the third term. one copy will be gone. So we'll have 1.03 squared, we'll have the 5 6 squared, and then the other pieces were factored out to the front. So what we get here is 1.03 squared times 5 out of 6 squared. And then this pattern is going to kind of keep emerging here. So essentially, the next term you could predict would be a 1.03 to the third times a 5 6th to the third, and then plus dot dot dot. This summation is going to go out to infinity here. So writing this in a way that lends itself to interpretation as a geometric series, all we're going to do here is group the 1.03 times 5 6th and treat that as sort of our increasing unit. Right? So we're going to treat this thing as the piece that we keep raising to successively higher powers. Okay? So we'll have plus, this will be 1.03 times 5 over 6 squared plus 1.03 times 5 over 6. This will be cubed plus dot dot dot. Okay? And again, it's these pieces that keep getting raised to successively higher powers. So when we apply our geometric series formula, get rid of this, sorry. When we apply our geometric series formula, we'll have 100, 1.03, 1/6, and then this inner piece is going to simplify to 1 over 1 minus the term that we keep raising to higher powers. So this will be 1.03 times 5 6th. Okay? Now we could jump to our calculator and figure out what this is approximately equal to, and we'll get, this is about 121.18. Okay, so for the last part of the video, I want to introduce our second random variable, something called the negative binomial random variable. And the basic idea here is to do the same thing as we did with the geometric, right? We're gonna take a Bernoulli trial, so something that's success or fail, heads or tails, and we're gonna keep repeating it, but we're not gonna wait for the first success. We're gonna wait for a number of successes. So we have a new parameter here that we're introducing, R. This is the number of successes that we're looking to achieve. And the random variable itself is going to record the number of repetitions necessary to observe the rth success. So how many times we need to keep flipping the coin until we get the 5th head, or maybe the 7th head, or the 8th head. So situations that follow this basic outline can be modeled well using the negative binomial random variable. There's two parameters, R, which is how many successes you're looking to achieve, and P, which is the probability of success on any individual trial. Now, keep in mind that if R is equal to 1, this is the geometric random variable. All right, so there's nothing, it's sort of an extension of our geometric random variable, this negative binomial. Okay? So again, P is the probability of success, Q is going to be our probability of failure, and if we think about what the space of this negative binomial random variable will be, in order to observe R successes, we have to have at least R rounds. So we're going to start in round R, and then it could go forward as R plus 1, R plus 2, R plus 3, etc. Here's our PMF, and I want to explain this just a little bit. The first thing that I want to point out here is that if we end in round X, right, and we've observed R successes, this P to the R is going to count up the probability of those R successes. This Q to the X minus R, those will be the number of failures. And so what we really just have to explain here is how we get this combination out front. And remember, this should essentially be the number of different arrangements that we could, in theory, have for how these successes and failures play out. So let's suppose we consider something pretty straightforward. So let's think of something like maybe an R is equal to 3, and the round where we hit that third success is X is equal to 5. Now, since we end in round 5, there has to be a success in that last spot. So this is required. And what we have here are 4 spaces, or in other words, x minus 1 spaces. And what we want to do is, since one of our successes is already placed, we have r minus 1 successes left to place. So we'd have 2 in this case, s and s, and then the rest of this is going to be failures. So this binomial coefficient comes from placing the remaining successes into the remaining places, keeping in mind that the final place has to be a success and has to be at the end. All right, so the way we do this is just we look at x minus 1, these are the remaining places after the last, and then r minus 1, these are the remaining successes, and we place them in the given spots. And this gives us our PMF for the negative binomial random variable. All right, so let's consider an example. So an insurance company offers a policy where they will cover the first 2 damage claims to a car, but the driver is responsible for any damage after that. So starting with the 3rd claim, the driver has to pay. So in a given week, the probability of damage to a car is 0.11. What's the probability that the first damage claim the customer pays, or in other words, the 3rd claim, or the 3rd damage, occurs in week 5 or earlier, right? So here's the idea. Each week is the coin flip, or the Bernoulli trial, and the probability of success is 0.11, where we view success as a damage occurring that week. Right? Or in other words, a success is somebody filing a claim for the week. Right, so then what happens here is we're interested in the 3rd claim. So R is going to be 3 successes that we're trying to find. And then the rest of this is actually a statement about the probability itself. So we'd write out as a model here, x is going to be a negative binomial random variable with an r equaling 3 and a p equaling 0.11. And then our probability asks, well, what's the probability that the week in which we first have to make a payment for damage on our car occurs in week 5, so it could be equal to 5, or something less. All right. So if we think about this in terms of our PMF, right, the space, keep in mind the space of x starts in week 3, right? That would be the first time we'd actually have to pay a claim, and then goes 4, 5, 6 out to infinity. So we're really just looking at adding up f of 3, f of 4, and f of 5. Now, unlike the geometric random variable, the negative binomial when r is not equal to 1 does not have a nice cumulative distribution function or survival function. So we have to do this the old-fashioned way. So we would think about x minus 1. Here, remember, x is the input to your PMF value. So x minus 1 would be 2. And then r minus 1 is your number of successes you're looking for minus 1. So our first one would be 2 choose 2. We would have p to the r, so this is 0.11 to the 3rd. And then 0.89 to the r minus x. So 3 minus 3 is 0. So that would be our first term. To that we would add x, with x is now 4, so 4 minus 1 is 3. Choose 2, r minus 1, the 0.11 to the 3rd, and now we'll have 0.89 to the x, or 4 minus 1, so this gives us our first 0.89. And then in the last case, we'd have 4 choose 2. Hopefully you're starting to get the pattern here. This is what we would add up. Now what I want to point out is that when you're doing these summations for your PMF values, there are certain things that are always going to be in your, or that you'll always be able to pull out to the front. Essentially, this probability of success raised to the R power, you can always pull out to the front. And then you can work with what's left over, which will be essentially a binomial coefficient, right? A choose combined with some power of 0.89. Okay, so if we were to continue this, let's pull off a little extra space here. Probability that x is less than or equal to 5, so we could pull out the 0.11 to the third. 2 choose 2 is equal to 1, and 0.89 to the 0 is 1, so we'll have 1. 3 choose 2 is equal to 3, and then we'd have 0.89. And then 4 choose 2, this would equal, what do we get? 3, 4 says 12 divided by another 2. This would be 6, and we'd have the 0.89 squared. And so now at this point we could go to our calculator and start figuring out what this equals. So we get, this is 0.0112 approximately.